So welcome to this course on which is the first course on VLSI design and CAD. So as you are all aware that this is a course which is offered by the students and faculty of the Advanced VLSI Design Lab, IIT Kharagpur, during every summer. So this course has been running for the last 3 or 4 years, in which it has gained in popularity, and every year the second year students who complete their second year, they queue up for attending this course every summer. And in view of the popularity of this course, we decided that it's high time that we went for an all out recording of this course, so that it becomes available to our students during the semester time also. And it is also likely that this course will be useful for students who join the lab or join any project related with the lab, and they want to quickly learn the art of doing digital analog designs, as well as what are the issues and the problems and the solutions in the CAD, which is used for designing these chips. So I call this a first course because we assume that you almost have no background on this area, except for some basic awareness of what the silicon industry is about and what chips are, and we do assume, however, that you have some knowledge on digital pulse and digital circuits, which I believe that some of you have already taken a course on that in your second year, and also some basic amount of electronics, which I believe is covered in your basic electronics course as such. So taking it from there, we want to teach you the basics of chip design, how a chip is designed from concept to final tape out. So as you may be aware that the Advanced VLSI Design Lab has the facilities for designing chips. We have the CAD tool flows of Synopsys, Cadence, Mentor, etc. And we also have a free fab support from National Semiconductor Corporation, who have been very kind enough to extend their support in taping out our chips. And we have in fact taped out more than about 50 chips in the last few years using the National Semiconductor Foundry. So to get started on this course, the title of the course is computer please. Computer please. Yes. So this is the course title, first course on VLSI design and CAD, and this is an introductory lecture on that. So I would like to start by looking at the evolution of electronic computing. So if we go back to the 80s and 90s, and I just now checked that many of you were not born in the beginning of the 80s. So what happened was that during this period, computation became free. Now what do I mean by computation became free? So initially, the very simple computers used to be inaccessible to the common person, because they were extremely privileged resources, and you would have to even in IIT, people used to queue up from 6 o'clock in the morning with a stack of punch cards, which they would submit to the computer center. They would run it on a very old Russian computer, and then in the evening they would get the answers also printed in a set of punch cards, right? So that was the kind of thing that people had access to at that point of time. And then I remember that somewhere down the line, we came to know that that electronics department at IIT Kharagpur has procured a state-of-the-art computer which has very good interfaces, and it was a paper tape computer. So the good thing about that was you could type in your program in a device which would print out that paper tape, and then that paper tape would get fed into the computer. The computer would do the computation and print out the result again in a paper tape, and that paper tape would be fed back into a printer which would print out the results, right? So final thing that you got was a printout of the results, and that was really great at that point of time. So from that, you have more power than you did on those computers. You have more power on your cell phone today. Your cell phone processor is more powerful than those processors that we had on those days. And then we graduated to better computers. We had a HP 9000 and an Hewlett-Packard 1000 series computer, and the languages also started improving. So we we previously had only Fortran supported in our computers, and now there was a new language called Pascal which was being supported by this. So the good thing about Pascal was that it supported recursion, right? But so we started writing our first programs using recursion. So we started writing factorial using recursion. You know, the thing that even today people start writing their first recursive programs is factorial of n. The peculiar thing was that you could compute only up to factorial 13 in that computer. If you gave the value of n to be anything larger than 13, you know, you would get a error saying heap stack collision. You know, that's typically because every recursive call is putting a copy of your variables on the stack, and it did not have more space than, you know, just putting 13 of those on the stack, and beyond that it won't work. Right? So that scenario has changed completely now. So that's what I mean by saying that computation has become free in that generation. What was the next big challenge that the computing industry had? The next big challenge was storage, because as the computation started becoming free, we started doing more and more computation, and therefore we were able to handle more and more data. But how are we going to store those data? Now, storing that data, you know, the amount of data that we have to handle today has grown by enormous amounts. Have you seen any of the data centers in any company? There are huge racks of disks, you know, which store, you know, tons of data. Can you imagine the kind of data which Google has to store? It's phenomenal, right? Even corporate houses like IBM will have enormous amount of data, in-house data, for their own things, starting from simulation data of their previous chips, thermal profiling data of their chips, and then more recently, you know, the biggest the biggest volume of data that you get to see is in bioinformatics. You know, where for even one human genome, you are going to need something like 700 CDs to store the genome sequence. Right? So that's the kind of data that we are talking about. So there was tremendous amount of pressure to bring down the cost of storage. Right? So that's what happened in the next decade, that storage became free. And I'm going to show you some very nice pictures which will show that how storage became free, you know, what I mean by that. So we used to have a 256 megabyte disk in the computer science department, which was so heavy that you would have to put it on a roller. So you could only, you know, it was on a trolley, and you have to drag the trolley from one computer to another for 256 megabytes of data, right? And now our pen drive has 4 GB, 8 GB. Okay, so that has also changed a lot. So storage has become free. What's the next big challenge? What are we trying to make, you know, more and more available today? And that is, we are trying to make communication free. So communication is the next big thing. Now it is beginning to happen. Okay, so now you see that people who never were able to afford a land phone are going around with a state of the art cell phone, right? So that's beginning to happen. But there are a lot of issues that needs to be resolved, and not all of those issues are technical in nature. For example, if you look at the way that we allocate bandwidth to the different vendors, so each vendor has so the spectrum that you have available for mobile communication is just this small, and even that small of spectrum is split among the different providers. So it's, you know, it's like that if you had a highway, and if you say that this lane is for Marutis, this lane is for Tata cars, this lane is for General Motors car, and you are not allowed to switch lanes, you know, that would be a very bad way of utilizing the space in the highway. But that's exactly what we are doing today using the spectrum. We are giving each of them a very narrow band of the spectrum, and we are not taking into taking into account the fact that not all of that is utilized to the same amount in every different parts of the country. Right? So better ways of managing that will evolve, no doubt. But you can see that almost everything is going wireless today. Right? So you have different wireless standards, and one of the nice challenges that has come up over the last few years is that on your cell phone, for example, there are at least 3 or 4 different wireless devices. Something which communicates with Bluetooth, is another radio which is going to communicate with GSM, and then you have other, you may have Wi-Fi in your cell phone. So all of these require their own devices, their own radios. So a good challenge that has come up now is, can we do all of this using only one radio device? So what is the challenge there? That this radio device will now have to transmit and receive on different frequencies, because the frequency that Wi-Fi uses and the frequency that GSM uses are different. And then that would mean that, do we actually replicate the hardware for this transmission and receiver? Because then that would again blow up the amount of hardware that you need on your cell phone. So people are trying to do this using software. So that's the concept of software radio, where you are going to run all these different standards in software, and the hardware devices are going to be reconfigurable by software, so that they can transmit on these different frequencies depending on the protocol that is being used. Right? So that's an interesting challenge which has come. So these are the 3 essential things that are beginning to happen, and we are going to see that how the VLSI technology is going to play a role in this. So can I have the computer, please? Computer, please. Compute, yes. This is a picture which is quite nice. This is the 1954 prediction of what the home PC will be in the year 2004. Okay, so this was predicted in 1954 by a gentleman. He said that this is how the home PC in 2004 is going to look like, right? And this is how it actually looks like. So this is a picture of the iMac. Have you seen the iMac? So so you don't have that box anymore. The usual box of the computer has been done away with, and everything actually goes inside this monitor. So the space behind the monitor, where you have all the USB drives and things like that, and this is all that you have, and you of course can connect a mouse if you want. Okay, so this is where it has gone actually, and so you can see that it has somewhat, outdone the expectations that people had 50 years ago. This is what I mean by storage has become free. I'm sure that you have not seen a magnetic tape drive like this, but believe me that when we first joined the department of CS, these were the tapes in which we used to back up all our files, right? So after doing our computation, we would back them up in these tape drives, and then if needed, we would again load them back from the tape drives into the computer and then use them. Okay, the thing that is being loaded on this plane is a 5 MB hard disk in 1956, right? So if that was the case in 1956, so it's not surprising that 256 MB would be on a trolley in the year 1986. And then we have this 4 GB pen drive, which is as commonplace as it can be today. Okay, so that's what we mean by that storage has become free. And this has not happened just like that. It has happened because we have moved from magnetic tapes to magnetic disks to flash memory. So there is a lot of technological changes that has taken place. And as you might be aware that here we actually record things in a magnetic medium. Here also there is a lot of physical movement of the hard disk, the head that moves across the hard disk. And on the other hand, this is purely MOS, right? So we are storing it in flash memory, which is in semiconductor totally. There is no magnetic, there is no physical movement of anything that is involved here. Okay. Communication. So that's the that's the old telephone that we see in the old Hindi movies. Okay, so I mean we used to use that in our childhood. That was the only kind of telephone that was there. And if you look at this picture, it shows you the total worldwide cellular phone subscriber base and how it has grown. So this y axis is in millions of number of subscribers, and if you see that the growth, as the curve suggests, is exponential. And if you look at the curve, similar curve for India, it's going to be steeper, because it has caught on very fast and grown at an alarming rate. And just to give you a nice example of the kind of things that India is facing here. So I have a friend who works for Reliance in the telecom sector, and he was once telling me that they were having a meeting with one of the telecom giants of USA. I will not name the company. So they suggested that they were coming up with a new technology that would improve the way in which you download different kinds of code into your cell phones. As you may be aware that cell phones regularly download code from different sources and execute that. Now they were saying that with this technology we can scale up from our existing number of downloads to something like 30% more and things like that. And then this gentleman pointed out that look, that is not enough, because the total download that you are saying that you can support with this over a month is the amount of download that we have in a day, right? So that's India for you. So that is a huge technical challenge. So don't think that working on technology for the Indian context is not good, because there are a lot of challenges which are unique to India. Okay, that includes handling the numbers in this size, but that's where we are heading to. Okay, every populated country is going to need that in future. So we have to generate technology which can actually handle numbers like that, right? Both in terms of the amount of volume of data, the volume of the cost of the technology has to go down, and several other issues which I am going to talk about. And this of course is where the technology has moved from the old telephone to this one, and it is a convergence of technology. The cell phone is not just a phone anymore, it is also a mobile computing device, right? So we do more and more tasks here, from checking emails to working on presentations to using spreadsheets, everything on the mobile phone. This is a picture which talks about interfaces. That is another area where we will see a lot of growth in the years to come. Okay, so the picture out here, these are the paper tape, the punch cards that were there previously. Okay, so your program would be encoded in terms of the holes in this punch card, and this is a very old punch card machine, hand operated punch card machine. So you can see can you see the company's name there? It's IBM. Okay, so that's how people would punch in. They put the punch card here and then use this thing, like a punching machine that you have today, to punch out the different programs on this punch card. Okay, so from that, when I said that we went into paper tape, so this is a picture of the paper tape. Okay, and this is a picture of an old keyboard. This is how they used to look like when we first came to the department. Okay, most of the keyboards were like this, and from there, where are we headed? We are headed to a Bluetooth laser virtual keyboard. So we don't want to carry the keyboard around with us anymore, right? So you just carry this small device out here with you, and that actually projects a keyboard on the table, and you can start typing on that keyboard, and the laser is going to detect where your fingers are and is going to interpret that, right? So this is available in the market today, it's not future. Where is then the future? The future is that this keyboard, mouse and things like that are becoming outdated. We don't communicate with each other using keyboards, do we? Okay, sometimes we do, because these days I hear that people staying in the same wing communicate with email. That so that's a different thing, but that's not where technology should be headed to, right? So there is a tremendous amount of research that is going on natural language processing and on human computer interaction, and that is not necessary just for us. It is necessary for people who do not have the education to really go into and use a computer. It is also necessary for people who are physically challenged. They do not have the ability to work with that. There is a research group in this institute, you may not be aware of, which works on developing technology for the physically challenged, and they have done some wonderful work under Professor Anupam Basu of the Computer Science Department on developing different kind of human computer interfaces for the physically challenged people. So that's where it's heading to, and in the future we hope that we will just have to communicate by voice or in a more natural language with the computer, and it's going to be able to understand that. It's beginning to happen, and it will happen no doubt in the future. So what makes all this possible? The core technology behind this is the science of designing and manufacturing electronic circuits. So this is what is this technology? It's an incredibly complex technology, but it has been made feasible through generations of research and practice. This is one of the areas in where fundamental research is adopted in practice with the quickest turnaround time. So a new technology comes where somebody does a theoretical development, in no time you will see that it has been adopted in practice. This is the good thing about this area. There is a very streamlined design methodology which is assisted by excellent CAD tools. That is what you will learn in this course, that what is this CAD tool flow by which from a concept of a chip we can actually generate that chip. And there is the other thing is a streamlined manufacturing, which is the actual process of taking what you do in design to the final silicon, right. So the thing that you will study in this course is how do you take it from a design to the final pre-tape out phase, where you have something which is called a mask, and then that actually is used by the fabrication machine, and that produces the final chip. But there is a lot of issues that are there in that last step, the step of fabrication, okay, and that has to be handled by experts. It's not enough to just have the designers go and do that fabrication. It's not as automated as we believe it is, and that is why a lot of semiconductor companies, chip design companies, are going fabless. Did you know that Sun Microsystems is a fabless company? They don't have a fab, but they do manufacture a lot of processors, right? Sun Spark processors, which are there in many of the workstations that you will see in the AVDL lab, right? So that is happening with many other companies. Many of the leading chip design companies that you will see in the years to come, they are going to be fabless. They are not going to have their own fab, and that is a good thing, because you see, from an Indian point of view, well, we don't have state of the art fabrication facilities in India, but that's not a reason why we should not work in VLSI design, because design and fab are becoming separate entities. And what will happen in the future, or is likely to happen in the future, is that fab will be handled by only a few select companies who will be totally fab companies, and the design companies are going to use their fab support, are going to pay for that fab to get their chips taped out from there. Okay, that's the model in which the future of semiconductor industry seems to be heading, unless there is a change in the trend. What are the, if you are asked that what are the three most important challenges that we have to handle in the semiconductor industry, the first thing is we need to lower cost. Now you might ask that the only thing whose cost goes down in today's market is the transistor. Okay, anything else, potatoes, apples, anything else whose cost goes down, have you heard of it? No. but transistors, yes, and it has been happening for more than 3 decades now, right. So that's a very interesting thing, but we need to make it more affordable. So there was a very inspiring lecture, I don't know whether any of you attended that, by the president of Texas Instruments India, Dr. Bobby Mitro. So he gave a very inspiring talk a few days ago in the institute. So what he was saying is that many of the technology that we have today, it is still not affordable enough to penetrate everywhere in India, right. For example, they are working on a technology which is going to allow people to do an USG, an ultrasonograph, in less than 100 rupees. That's the kind of challenges that we have to face, because people will not be able to afford something like 700 to 1000 rupees for a single USG. Then it is not going to penetrate into the majority of Indian population, right. So when we talk about cost, that is the kind of cost reduction that we have to look at. The second, and it's not from a point of view of business, it's not bad, because the numbers will be so large that if you can lower the cost, your profit margin is going to increase, right. It's not that you are going to do only voluntary service there or doing social service there, okay. The second thing is lower power. Why do we want to lower power? Okay, so I have a complete slide on that, so when we come to that, we are going to talk about that. And the third thing that we want to do is we want to develop technology which is going to change the face of humanity. So far technology, the electronics technology, has been more in the area of entertainment, in computation, in communication, but not much beyond that. Now what we are seeing is that the penetration of the electronics technology in the bio area, for example, is growing rapidly. So medical instrumentation, that's a very exciting area to be in, because and one of the things in which Dr. Mitra was referring to in his presentation that day is they are trying to build a chip which is going to sit near the optic nerve of a blind person. It's going to capture the images using a camera and cause the same kind of sensation on the optic nerve as your retina would do, and is going to enable the blind person to see. And they actually have a proof of concept of that, which is phenomenal. That's what I mean by changing the face of humanity. If you can make a blind person see, that's great. So that's where we are heading to. This is the picture which you will see whenever you hear any talk in the silicon domain. So this is the Moore's law. What Moore's law predicted was that every 18 months the density of transistors in a chip is going to double. So if you have the chip of the same area, you will be able to pack in double the number of transistors on that chip every 18 months, right. And no one believed that that was going to happen when it was predicted, but it has been holding good for since 1970. So that's a large number of years have passed by, right, almost 4 decades, and it still holds. So this shows you the number of transistors that you have on a chip. So at the top of this is you have the Intel dual core Itanium 2 processor, then you have this Itanium 2, and then here you have Pentium 4. So as you can see that the growth has continued unabated for so many years. What has that resulted in? The transistor geometry has shrunk, and it has shrunk to such an amount that we are beginning to see quantum effects, right. So we are getting down to the almost to the atomic level, right. So the question is that where are we headed next? I mean, can we still continue this kind of growth, or do we have to look at some other alternatives? And the opinion is still divided. People believe that we can sustain this growth for at least 10 more years. Okay. This picture shows that how the cost of transistors has gone down. Okay. So as you can see that this is the cost per million of transistors. Okay. So this is not the cost of one transistor, by the way. This is the cost per million of transistors. Okay. So from 1965 it was, and you can imagine that because of this, when we joined IIT sometime around here, okay, so then a million transistors would cost something like $100, right? But what we would have here is that if you have a chip having only 4 NAND gates, you would have to sign the register, issue it, and before you turn the power on, you would have to have someone come and check it that you have put the power in the right places, right? So people did not want that 4 NAND gate chip to get burnt because it cost an enormous amount of money at that during those years, right? So from that, I think today you have access to much larger chips, and people don't bother too much about you making a mistake, and would probably prefer that you make mistakes so that you know that you can do it right the next time. This picture shows you the way the power density has grown. So starting from, so these are some comparing things. So we have rocket nozzle right up here, and by the look of it, that by 2010 we will be up there, right? So your chip is going to heat up to the same temperature as a rocket nozzle. Now obviously then we will really have to have enormous cooling technology to prevent that from happening. So why do we have this kind of power requirement? So if you look at the Pentium series processors, they are approaching the kind of power that a hot plate, the plate in which you do a cooking, the cooking range, it heats up to that kind of temperatures. Why? That is because there is a huge number of transistors. These transistors will change state, you know what I mean. So that switching is going to charge up the capacitors, the parasitic capacitors, and the capacitors between the drain and source and the gate and drain. Okay, so those are going to, what happens is that keeps on changing very rapidly. So in one cycle, your chip might be drawing something close to 5 amperes of current. In the next cycle, it might not be drawing any substantial amount of current at all, right? And that is because that the switching patterns can be widely different from cycle to cycle. What does that mean? That means that designing the power supplies for these chips is an enormously complex task. Why? Because it has to source a large amount of current in one cycle. In the next cycle, it just has to bring down the current to nothing at all, right? Now that means that these power supplies, which are supposed to hold the voltage very steady at a given level, will have to have extremely smart control so that it doesn't pull down the voltage. Because if you take any normal power supply and if you suddenly draw a huge amount of current from there, it is going to pull down the voltage, right? So one module in this course is going to focus on power regulators, the regulators which hold or which are the power supplies to your chips. Okay, and there is a very strong group in the VDL lab which works on designing these power supplies. A typical cell phone chip, a cell phone is going to have a power management chip. What does the power management chip do? It contains several such regulators packed into one chip. Okay, and that supplies power to the different components of your cell phone, and these components require different voltages. So some of the components might be working at 3.2 volts, there might be another which going to work on 1.85 volts. Okay, so each of these components are going to require different voltages, and the power management IC is going to produce that. Not only that, the power levels of these different components will change with time, because today in order to bring down the power, we switch off different parts of the chip when they are not in use, right? So for example, your chip might have two processors. When one processor is not in use, it can be put to sleep, right? What do we mean by putting it to sleep? There are various ways of putting it to a low power state. So one of them could be that we simply shut out the power. But shutting off the power means that you lose the state of the processor. So if you want to do that, you have to first save the state of the processor and then shut out the power. You might choose to do something as that let us not totally shut out the power, let us reduce the power level so that it is able to maintain its state, but there is not going to be any switching in the chip, because in that part of the chip, because it's not active at that point of time. So it's going to retain its state, but it is not going to eat up too much of power, except for the amount of power which is needed to retain the state, right. So people use things like clock gating, where you shut out the clock from that power island, or they can use something like voltage scaling, they can reduce the voltage level of that. Now what would that mean? That means that the power supply or the regulator which is supplying power to your chip must support multiple voltage levels, so that it can operate on those different voltage levels, right. So these are issues that are there, and people do a lot of power management in their chips today. That's a major area of research which is has been there for quite some time now. The other thing that people want to do is they want to make sure that when you are laying out the different components of your chip, you want to place them in such a way that the ones which are going to be more active are not adjacent, because if they are adjacent, then the region in between them is going to heat up a lot, right. So people start doing this right from the architecture level. So when you are thinking of designing a chip which has 4 processors, so it's going to have 4 processors, it's going to have several cache blocks. So you decide at the architecture level only, where are you going to place these processor cores, where are you going to place the caches, how are you going to interconnect them, so that the total, you don't create hotspots inside the chip. And do you know that when you actually your processor, be it the Pentium or any other processor, it spends a substantial amount of time in thermal shutdown mode. You don't get to see that. The processor is running, you see the computer is working for you all the time, but there are a lot of time in between when the processor is actually not doing anything, it is just cooling down. And there are things like thermal viruses. You heard of thermal viruses? These are viruses which are going to pump instructions into your processor in such an order that it is going to create hotspots inside your chip. So typically in a normal program, normal kind of computations that you do, you may not see exactly that sequence of instructions coming into your processor. But maliciously someone will write a program which is going to generate exactly that sequence of instructions, which is going to heat up one part of the chip and try to burn it out. Even if it is not able to burn it out, because you will typically have thermal protection, you will see that your chip is spending most of the time in thermal shutdown, because whenever it runs, that virus starts running, it heats up the chip, and again it has to go to thermal shutdown to cool down, right. So people are designing thermal viruses not only because they want to protect their processor from that, but because during the design you want to see that under what worst case scenario is your chip going to burn out, or it's going to underperform, right. So it's not that people are just writing it for malicious purposes, it is also for design purposes. And you will see increasingly there are a lot of different applications where we model the problem as a game, and we model the adversary as a malicious person who tries to scuttle your optimization. And in CAD you will see more and more of these problems that are coming up, which are being modeled by games, right. And there are leading companies who are hiring people who are experts in computational game theory to do this for them. This is a indication of the kind of cooling that people have to do on the computers today. So this picture on the left is a picture of Cyber 180-840A CPU. We had one of the Cyber computers in the computer center previously. It used to run on a technology called ECL, emitter coupled logic. I believe some of you are aware of what is emitter coupled logic. So it's not TTL, it's not MOS, it is ECL. ECL works very fast. The switching speed is very high, but it eats up a lot of power and an enormous amount of power. And if you have a big computer like this one on the left, which is going to run on ECL, then you need to have an enormous amount of cooling. So these pipes that you see are actually cooling pipes. They are pumping in, you know, uh, coolants, okay, at a very low temperature through these pipes, and right on top of the circuit boards you will see those cooling pipes running all on top of the circuit board to cool down the chip below it, right. So that was you could actually go to the cyber and see that, and it's a fantastic sight to see, and you can understand the amount of heat that it generates during computation. When you go to a data center today, you will see that cooling the data center is a major problem, because you just pump in as many air conditioners as you can in that room, and it still is really hot when you are inside. Why? Because there's so much of computation that's taking place all the time. So that power is, as we just now said, it's phenomenal amount of power. This is a cooling system for a motherboard, right? So can you see the processor? You can't, because the fan is sitting right on top of that. Okay, so if you open up one of your Pentium 4 based PCs, you will see exactly a similar kind of picture. The Pentium is covered on top by the fan, or on the side by the fan. It just keeps on blowing the air on it. This is another kind of cooling where you don't use a fan, but you use a set of plates which is expected to dissipate the heat from the board which is down there. So you see all that miniaturization that we have done here, and then you have this huge cooling tower sitting on top of that, right. Now that's something that you can't do on a cell phone. You can't do that on a cell phone. You can't put in this huge tower of these plates or that fan inside your cell phone. And we are going to need a lot of computational power in our cell phones in the years to come. So what are we going to do about that? How are we going to cool down the cell phone, right? So a lot of power management is going to be needed, because we can't really put all those kinds of cooling techniques on this. There are new kinds of cooling techniques coming up, like microfluidics based cooling techniques. What these do is, they, on top of your wafer, you put in another wafer which is going to run small drops of coolants into appropriate places on top of your chip, and it's going to evaporate there because of the heat, and it's going to draw the latent heat out of the chip. Okay, so it's inside the chip, it's not outside the chip anymore. Okay, there is a group in IIT Kharagpur in the mechanical engineering department who are doing very good work on microfluidics based chip cooling, and there are state of the art facilities, research facilities which are working on that. This is another very nice area of work where chip cooling is the main issue. So if we look at the chip design flow from concept to market, so these are the four main parts of it. So we start with the specification of what we want to design, then we go to the implementation. This is the pre-silicon implementation. So pre-silicon, by pre-silicon we are going to refer to everything that happens before you tape out your chip. Okay, so this is the main design part, and then we typically sometimes go for a prototyping, and there are different platforms for prototyping like FPGAs and things like that, where you prototype your design and then do more validation there, validate that the chip is working correctly, and then finally you go for manufacturing. And in manufacturing also, you have first silicon which you want to test rigorously to make sure that it does not have any design defects, and go through the iteration until you get the silicon correct, and then we are confident that your design is correct, the silicon is working properly, then you go for manufacturing. But manufacturing, post manufacturing also you need to test. Why? because the manufacturing process is prone to errors. No, that depends on a whole lot of things, from the errors that the fabrication machine introduces to various other factors which take place during the fabrication process. So, in spite of all this validation of your design, after the chip is the chip is manufactured, each chip has to be tested. But you can't do all that testing that you did in the first silicon. You cannot repeat all that test on each and every chip, because then you will never ship it in time. Yes. So, you have to do a reduced set of tests, and that again is a very important challenge, that which test do I keep for post manufacturing testing. Okay. So, let us look at what are the broad considerations, what do we want to optimize when we want to do a VLSI chip design. So, let us take a very niche example, that suppose we want to design a chip for a pacemaker. Now, first thing is that we want to minimize the delay that the chip incurs in responding to the inputs that it receives, because obviously if it has to be a part of a pacemaker, then we have to have our timing absolutely right. The chip delay should not be such that if there is a problem, it takes too much time in reacting to that. Okay. So, let us count this as for the most primitive objective, that we have to minimize the delay. When we want to minimize the area, we want to make the chip as small as possible, because we have to implant it inside the body of the patient, right. So, we do not want to have a large implant. So, we need to minimize the area. Okay. Third thing is we want to minimize power. Now, here the power minimization is not because of cooling, but because we want the battery to last as long as possible. We do not want the person to go through that operation every year, right. So, we want, the problem is that battery technology, though it is also going up, but it is not being able to keep pace with Moore's law. So, the amount of power that the new chips are taking up, to sustain that amount of power for the same duration, we need much smarter batteries, and that does not seem to be happening to the extent that we would like it to happen. So, that is why we have to minimize the power on the design itself, so that with the same battery we are able to run it for a longer amount of time. Okay. So, for cell phones and others, we know we do not want to keep charging the cell phone every day or every hour, right. So, that is why we need better and better batteries, we need to have low power devices on the cell phone. But in cases of medical cases like pacemaker, we need to have that pacemaker, the battery to last at least 15 years if possible. Verifiability, this is a very important thing. 70% of the chip design time is spent in verification. Why? Because we are making the design more and more complex, and we have made it so complex that it is hard to verify that whether it is absolutely foolproof or correct, right. So, we will study verification in some of the lectures in this course. In case of a pacemaker design, we cannot tolerate any design errors, right. There was a recent meeting which one of my colleagues had with Bosch. Do you know what Bosch does? They design chips and they design components for automotive companies, right. So, when Bosch goes for either manufacturing or buying out electronic components, typically when we have electronic components like chips, etc., one of the specs items of a chip is the failure rate. Okay. The failure rate indicates that how often can you allow the component to fail. For automotive electronics, that has to be 0, not 0.00001, it has to be 0. Why? Because if something goes wrong, someone is going to die, right. So, that is the kind of challenge that one has to live up with. that when you do a design, you have to be dead sure that it's going to be correct. So what kind of verification can we do to make sure that that happens? This is an extreme case. For many other cases, we don't do this. It is not as bad in software industry. In software, you can have patches. In a chip, you cannot put a patch. Okay, so that's the bad thing about the silicon industry. People are trying to do things like, if you have bugs in the first silicon, they are trying to work around and just modify the silicon a little bit so that you can get a correct version of it. But you can't do that in huge amounts, right? So it's a very very sensitive area, and one mistake in one of your most popular chips can totally bring the company down. And the Pentium bug, I mean, Intel survived that because it was only Intel, right? So many other companies would not have survived that. So the next thing is improving reliability. Now that's what I actually meant when I was talking about automotive components. That component should not fail under any situation. That situation would mean that under different thermal conditions, under different kinds of usage, it should never fail. Testability, this is another important thing. We are going to integrate a lot of third-party components into our future chips, right? Now, if you import a third-party component and put it on your chip, you have to make sure that it is going to work in the context of your chip also, right? Or in other words, whether that component is indeed doing what it is supposed to do. So for that, what we need is, we need to have hooks inside the chip so that you can test individual blocks and you can test the whole chip as a whole, right? So testability is an important criterion, and you will be surprised to see that there is a significant portion of your chip area which is used up by the test structures, the structures which enable you to test the chip after it is taped out. If you don't leave those hooks, your chip will not become testable, and then you would not know that whether it's functioning correctly or not. And if in case it is not functioning correctly, you would not know where or which part of the chip is not functioning well, right? So that this is another important criteria. And then it has to be affordable for everyone. So on top of all this, you have to do all this and then still keep the cost down, right? So as you can see, there is an enormous investment in terms of technology, optimization and computation that takes place in all of these steps, and that involves manpower, it involves research, etc. And then the final product has to be as cheap as possible, so that we break the so-called digital divide, that people who can afford it and people who cannot afford it, that margin has to go down. Now, what do we want to study in this course? So what are the things that people would like to have? So let us look at what's going to be the future computation platform, the chips of today and tomorrow. So we are not going to have pure digital chips and pure analog chips anymore. They are going to be there, but the future lies in mixed signal chips, chips which have both digital and analog. That's why who are the computer students, computer science students here? Yeah. So you guys, I'm sure you don't like analog very much. Neither did I when I was in my BTech. But then you have to be aware of the issues in analog design. Otherwise, your chips, or when you work if you work in the semiconductor industry, you'll have an incomplete knowledge of the whole picture, right? Similarly, the analog guys, it's nice to design circuits with a few transistors, but then you also have to know what happens on the other side, on the digital side, when people have to deal with some billions of transistors, right? So you have to know what are the effects, what are the challenges, etc. So this is a typical platform where you have the processor, you have the memory, which are typically connected by a high performance bus architecture, and then you typically have a bridge to a low performance bus side, where you have all the different components. Some of them can be digital components, some of them can be analog components, and they can have digital interfaces to interact with the rest of this. So this is a kind of architecture, and then you will have power management, which is going to manage the power in this whole picture. It is going to decide which block is going to have what kind of power and at what point of time. So that's why this course is going to talk about three different facets of the silicon industry, namely analog and RF design, digital design, and CAD. Okay. The design flows in these two are quite different. So let us look at the digital design flow, which is on the left side, and the analog design flow, which is on the right side. So let's see what are the steps in the digital design side. So there we typically enter the design in a high level language, and the popular languages today are Verilog and VHDL. And then from there we do a behavioral simulation. We run this language. When you enter the circuit in this language, you can simulate that circuit, right? What is this behavioral simulation? So for example, you want to design a processor. So you will enter the design at a level which is called register transfer level, and then you will do behavioral simulation of that register transfer level code using simulators. And can you imagine the kind of simulation that people do for this kind of processors? The simulator is going to simulate your processor, right? So you are going to boot an operating system over the simulator. So the simulator is just simulating the chip. Okay, you run the complete Linux operating system, for example, on top of that, right? Remember that at the bottom you don't have the hardware, you just have the simulator, and on top of the operating system you will typically load something like Oracle or some database application, and then run a set of custom applications on top of that. This whole stack is going to run on top of the circuit simulation, which is going to simulate every component of your processor, and this simulation runs into months, right? And when you have design errors, you go back, correct them, and then again do this, right? The enormously difficult tasks are that when you find a bug during the simulation, you have to map it back to where the defect is, then redo the design in that part, and then again go through this. And if low down the design you find that there is a major architectural flaw in the design, then that's a very bad news for the company. Then once you are confident about the design, then you go through what is called the synthesis. So synthesis is actually taking the design specified in that language and translating it into your gate level design. Okay, now gate level design is going to do what? So the initial thing here had the logic, the intent of what you wanted to do, and that intent is implemented in terms of your gates, right? So there is a lot of logic optimization that will take place there. You want to minimize the number of gates in your circuit. So there are a lot of tools which are going to do this synthesis for you, and you are going to learn to use those tools in this course. Okay. Then after synthesis, you have to do place and route. So for the individual blocks that you have synthesized, you have to place them on the chip floor. You have to decide which is going to go where, and then you have to route them. What is the meaning of routing them? Each of those blocks are going to have certain signals at the interfaces. These signals have to be interconnected between the blocks, right? So that is called routing. Now you just have this much amount of area for placing the chips, for placing the blocks. So you want to pack them as close as possible and in as little area as possible. That's a geometric problem, and there is a lot of geometry that goes behind the placement and packing of the different things there. But placement is not guided solely by the desire to optimize area. You also have to leave space for the testability. You also have to make sure that you don't create thermal hotspots, right? And you also have to make sure that you are not placing it in such a way that your wires cannot be routed properly from one block to another. Otherwise, you will have too many interconnects, and interconnects, if they are long wires, they are going to have all kinds of capacitive and inductive effects, right, which is going to bring down the performance of your chip. So in spite of all the synthesis, all the timing optimization, if you go wrong in this step, then you will see that finally the chip is not being able to meet your timing requirements. And what would that mean? That you planned for a 4 gigahertz processor and you are ending up with a 30 megahertz processor, right, because you are not being able to run it at a speed higher than that. That's bad news. So these are these steps that you see here, they are not unrelated. Then we do post layout simulation to make sure that all your design rules, etc., you make sure that at the silicon level everything is fine, and then you do a full chip assembly. So this is typically done for individual cores, and then you connect the cores together to do a full chip assembly, a full chip design rule checking. What are design rule checking? There are certain rules about the kind of things that you can, the way in which you can place the silicon and the metal on the actual chip floor. There are design rules for that, okay, depending on what technology you are using, and those rules are different depending on whether you are doing whether you are taping out in 180 micron 0.18 micron technology, or you are going for 25 nanometer technology or whatever, okay. So and then you do a full chip simulation, and believe me that for large designs the full chip simulation is almost a myth, okay. So there is hardly anything that you can do there, but still people do it in different pockets, and then you go for tape out. Now the analog design flow is completely different from this. That is because that here we are dealing with something like few billions of transistors. On this side, the typical analog modules is going to have only a handful of transistors. But then why is analog design also a very difficult art? That is because we have a lot of automation on this side, because here what we want is a correct design, okay. What we want is specified in terms of logic, and each of these steps is transforming the design from one level of abstraction in one logic to another level of abstraction in another logic, right. So and the underlying logic in this whole thing is Boolean, right. So that's why you have nice algorithms for doing all these steps on the digital side. But in analog, it is not just about doing things correctly, it is about doing things well, okay. So you can have two designs, both of which meet the specs, but one of them is a good design, the other one is a bad design. Now we can always refine the specs to such an extent that only the good design will prevail and all other bad designs will be eliminated, but a priori, because there are many different criterions involved, it is very hard to predict that exactly what specs is feasible. So you would leave a sort of broader specs, and the underlying understanding would be that you have to design it well so that it does some good things in some good ways, and these good things quote unquote and good ways quote unquote will vary from design to design, which is why analog design is considered to be an art. It's not just, it's science, no doubt, but it's also an art to get it. That's because there is a lot of intuition that goes behind doing an analog design. We have not yet been able to automate it to such an extent that we are able to automatically synthesize analog design. So then, is analog CAD a myth? Is it never going to be there? So for that we need to understand one thing, that CAD is not to replace designers, it is to help designers. So even the analog designer spends time in iterating through a set of options, changing some parameters here, there, tweaking some of the geometries of the transistors, and then trying to reach the specs in a better way. Wherever those tweaks are done and wherever there is not much of intuition behind those tweaks, we can use automation. we can say that, hey, let us do the tweak automatically, and then let us again run the simulation automatically, and then you tell me which tweaks I should do, and then let me do that in the background. You come back in the morning and I show you the responses for each of those tweaks and how the circuit behaves for each of them. Now that's where analog CAD is going to come up, and it is beginning to take shape in some of these steps. For example, analog design starts by using what is called a schematic editor. So you just go to a graphical editor and you start designing there. So you enter the schematic. Now the schematic could be drawn at the transistor level. It can also use some standard cell blocks which are pre-designed by other people and provided as part of the tool, or provided as part of the library that your company has built over the years. And then after you have designed using those blocks and the transistors and the components that you have entered in the schematic editor, then you do a SPICE simulation, and then from there you go to a custom layout. Now there is this schematic driven layout option that is increasingly being used by analog designers, where you do the schematic entry and then automatically you are generated a custom layout. So this layout is being automated to some extent, and then from there you go for design rule checking. Then you extract out the net list from the design and then do a post layout simulation, and after that the remaining part is just like the digital design, except that you see that here in the future generation we are going to integrate the digital and the analog together. There are some intermediate hooks here which I have not shown, where you can actually do a behavioral simulation and a SPICE simulation of the analog together. So there are new kind of platforms where you can have the analog part in the transistor level, you can have the digital part in Verilog or VHDL, and you can simulate them together on a mixed mode simulator. Okay, so that helps you in doing a lot of verification earlier in the design flow, and then the analog flows takes this part and the digital design flow takes this part. Okay, this is the agenda of the course. In the first 2 weeks we are going to deal with the common topics, where the next lecture is going to be the introduction to VLSI by the senior most faculty in our lab, Professor N.B. Chakraborty. He is a retired professor from the electronics engineering department, and he has been very kind enough to kick off the course with an introductory lecture, which is the one which is to follow immediately after this. And then tomorrow you are going to have the introduction to MOS fundamentals and device modeling. I believe most of you are familiar with MOS, but this is going to brush things up and then give you some more details on that. Day after tomorrow we are going to have a lecture on basics of digital design, okay, where things like ASIC design, architecture design and low power design, these are the things that are going to be covered in some of the lectures in the first 2 weeks. Okay, so these are typically going to be delivered by the professors who are going to introduce these areas to you, and what are the main challenges, what are the issues, and how people are tackling that. In the analog design also you are going to have common topics on amplifiers, current mirrors, voltage references, and introduction to RFIC. Okay, RF is also an important thing, and increasingly we are going to have more and more RF built in onto your chips, right. So that's an area in which an introduction is very much important for everyone. And in the CAD section we are going to have lectures on introduction to digital CAD and introduction to analog CAD, and you are also going to get introduced to Verilog and the synthesis mechanism that takes place for digital circuits. This is a common part for both of you. And then in the analog track in the weeks 3 and 4 you are going to have switch capacitors, comparators, IO buffers, then how analog layout is done. You are going to have some lectures on behavioral modeling, which is a very new topic in the analog domain, where you model analog designs at a higher level of abstraction, make sure that they are correct, and then synthesize the analog designs manually, of course, and make sure that the The good thing about behavioral modeling is that you can make sure that your whole chip is going to work together with the other components in the digital side before you actually start embarking on the design of the analog blocks. So there is a huge activity in behavioral modeling, research activity, which is ongoing in the institute, in the lab. Then you are going to have lectures on communication circuits, on transceivers, microwaves, and then a set of lectures on power management ICs. This is a very niche area, but a very important area and upcoming area in the analog side. This is the agenda for the digital track on the weeks 3 and 4. We are going to have RTL simulation and verification at the top level, and then you will have CAD for all the 3 levels, high level synthesis, which actually takes the design in the Verilog or VHDL and then synthesizes the design into logic, then logic synthesis and logic optimization, and then physical design, which is going to talk about layout, placement, routing, etc. Parallelly, you are also going to see back-end design and tool flow. This is, all these steps. Here you are going to talk about the CAD algorithms and the way that this is implemented by the tool, and you are going to use the tools when you go through the lectures on back-end design and tool flow. Then timing and power analysis of the chips is going to be covered, both from a CAD point of view as well as how you actually do that in the design. Then there is going to be a lecture on how processor designs take place, FPGAs and prototyping flow. How do you build a digital design and then prototype them on an FPGA, and then test and design for test, okay, of digital designs, and a few lectures on formal methods for design verification. Okay, so that's I think you realize that your work is really cut out for the next 4 weeks. So I hope that you have a nice time and you learn a lot. And the main intent of this course, I hope that is going to be successful, is in drawing many of your interest to work in this domain in the future. So let's hope that after this course we keep on seeing your faces in the lab, in different projects, and associated with different people who are working in this broad domain. Okay, thank you for your attention.